There are no waveform runs, right?
No, not as such, but you
It's
know,
mostly the harmonics calculation.
the harmonics calculation, THD, knowing
Like
the
the
difference
homework.
between, knowing the differences between unipolar and bipolar, PWM, applying the equations to calculate the harmonics in the different cases, right? So, uh, I mean, if you understand how to use a comparator to create PWM, for example, right? And there's besides that, there's no
Okay.
right. Okay, so last time we sort of stopped a little bit after this. I just want to review here again. So again, the tool that we will always have to utilize is to look at waveform quality is Fourier series or a Fourier transform extension, right? So what we did here, what they've been doing here is, for example, for the bipolar or unipolar switching, you have many pulses, right? They take each one pulse and define it by a set of angles, and then if I change this angle, is that also an indication of changing my amplitude modulation or not? What is amplitude modulation? Amplitude modulation is the ratio between the reference sine wave and the triangular waveform, right? So here, if we look at amplitude modulation is sort of an indication of the magnitude of my output, right? It's something that indicates the magnitude of my output. How is my output magnitude controlled? It's controlled by the intersection of my sine wave, my reference waveform, with my triangular waveform, right? If the sine wave is large, then I expect to get a large output. If the sine wave is small, I expect to get a small output, right? So the ratio between this sine wave reference and this triangular high frequency carrier reference, one is the reference or modulating waveform, and one is the carrier waveform. The ratio between them is an indication of the amplitude of my output, right? So I would like to control this to control the voltage value, right? So how do you control this? We said you're going to change the value of your duty ratio, which is your sine wave, but your triangular waveform will never be the same. Will always be the same, right? So the carrier triangular waveform never changes. It's always the same. This is always the same, the carrier waveform, and then you're intersecting it with your reference. Your reference will take on different values depending on what output you would like to see. You would like to see a large output or a small output. So if I change the magnitude from case 1 to case 2, remember, where are these two going? These two are going to something like a comparator, right? The triangular wave here, the sine wave here, and then I get outputs depending on if this is my plus or minus or vice versa, right? If now if I put my sine wave here at the plus terminal and the triangular wave on my minus terminal, then whenever the sine wave is greater than the triangular waveform, I get a high. Whenever it's lower, I get a low. And then I can reverse it. If I want to reverse it, I can do that, right? So the width here, the width is controlled by the intersection of the sine wave with my triangular waveform, correct? So, and this width defines several angles, right? This width defines the angles that are used to calculate the Fourier series for each pulse, right? So this pulse here, I want to do the Fourier series for it. How do they do the Fourier series for it? They define it using a few angles, right? And then they come up with the Fourier series for this single pulse, defined by these various angles that they showed here in the drawing. Okay, so this single pulse K, is contributing to the harmonic content of the waveform, whose nth harmonic is Vn. Right, so I have a waveform that has many harmonics, V1, V2, V3, V4, V5, whatever it is, right? I would like to find the Fourier series. So I'm using each pulse to find the effect of every pulse on the Fourier series of the waveform. So from that Fourier series, remember, from Fourier series you can find the harmonics of a certain waveform, right? So that's what they did here. So this is the Fourier series for this single pulse and how it affects the Fourier series of the total waveform, right? If I now take this pulse and the one next to it and the one next to it and the one next to it for the full period, I sum them up, I get the Fourier series for my waveform. Does it make sense or no? I mean, I can only get the Fourier series for a periodic waveform, right? This pulse is periodic in every cycle of the fundamental output of this pulse width modulated waveform. So I will find the Fourier series of this pulse, right? And then for the one next to it, and then for the one next to it, and then I'll have my full period. Then add all of these Fourier series results up, and I will come up with Vn. Vn is something we use to calculate the first harmonic or third harmonic of the full waveform. So, but to calculate the fundamental of this waveform, how do I do that? I have to calculate V1. V1 is equal to V1 of K, where K is 1 or 2 or 3 or 4 or 5. What is K? K is each pulse that is creating the full period. Does it make sense? So I have K pulses here. These are K pulses. These are pulse 1, pulse 2, pulse K equals 1, K equals 2, K equals 3, K equals 4. This is periodic because I have it here, and then I have it again here. And then I have it again in the following period. So it's a periodic pulse that is defined by a few angles. These angles are what we've defined here. So for that single pulse, I found the Fourier series. Now I want to find the Fourier series for the full waveform. I have to add the Fourier series for all the pulses together, right? Because after that, I can tabulate. This is what? This is V1. This is V for n equals 1. How did I find V for n equals 1 at various modulation indices? A modulation index is an indication of the intersection of my sine wave with my triangular wave. The higher the intersection, right, the higher the modulation index. The lower the intersection, the lower the modulation index. So what are these intersections going to result in? They're going to result in different angles. They're going to result in different angles. If this is my sine wave here, this is my sine here. If I bring this sine up, if I bring this sine up here, it will change the intersection, right? The intersection will be now here. The intersection will be here. Intersection will be here, right? So I will get a pulse that looks like what? Get a pulse that looks like this. Right? If I change the magnitude of my sine wave, right? So now I've changed my pulse. I've changed the pulse width, and I've changed the angles, right? But the pulse is still defined by the same 4 angles. 4 angles are defining the pulse. So we found the general equation for a pulse defined by 4 angles, the Fourier series of a pulse defined by 4 angles. That was this one. I have many of those. I just add them together to find the total Fourier series of the waveform. Right? That's what we did here. And then here I just tabulated the numbers after dividing them by VDC. So if I divide by VDC here, I just tabulated this number. So V1 is equal to what? V1 at a certain modulation index equal to 1 is equal to 1. So that's when I calculated V1 here. It happened to equal 1 when the modulation index was equal to 1. The modulation index is controlling these widths. What are the corresponding angles for the various widths? They didn't tell us here, right? They just, when you're asked, if you're asked to do that, you'll be given the angles, and you'll be able to fill in here and calculate, V1 corresponding to a certain pulse. You have 4 pulses, then you calculate the V1 corresponding to this pulse, this pulse, this pulse, and this pulse, and you add them up. That's what they did here. They just did that for you and tabulated the results. The new thing here is when they did this for all the harmonics, 1, 2, 3, 4, 5, 6, 7, all the way to infinity, what they found was in bipolar PWM and unipolar PWM, we get different spectrums, harmonic spectrums for the output voltage. The output voltage magnitudes differ when you look at bipolar versus unipolar PWM. They calculated the Fourier series coefficients for all numbers all the way to a large value. And they found that in bipolar PWM, your first harmonic is at the fundamental. That's a good thing because you want to do that. You want to create a fundamental. And then they did 2, 3, 4, 5, 6. All of that was 0, which is great. Do I have a third harmonic? I don't have third, fifth, seventh. So it's wonderful compared to the stuff that we had before. You know, the single pulse or the 50% duty ratio stuff that we initially had. That stuff had third harmonic, had fifth harmonic. If you go back to that stuff, yeah, it had third harmonic and fifth harmonic. Remember, we were canceling the third or the fifth, or the third and the fifth together. So it had third, fifth. So it had a lot of low order harmonics, which are very detrimental to your system, right? They will cause harmonic currents, assuming there's a load or harmonic impedance. Yeah. But with sinusoidal PWM or with pulse width modulation, and this is called sinusoidal pulse width modulation. Why is it called sinusoidal pulse width modulation? Because I'm modulating using a sine wave. It's called sinusoidal pulse width modulation. Yeah. So what we found is this thing is really doing a lot of interesting stuff because my first harmonic is my fundamental, which is what I want. After that, I don't see any low order harmonics, so I don't have to worry about large bulky filters anymore, right? Why can't I use that for all power converters? Because all power converters cannot switch very fast. Because if you're developing a power converter for using a thyristor, for example, like something like Qatar Steel uses, you cannot put many pulses per half cycle. You're limited to 1 or 2 pulses because of the speed of the thyristor, and I will show that later, right? So because of that, you're limited to a certain simple switching mechanism, like the single pulse per cycle or 2 pulses per cycle. If you have 5 fast switching devices, then you can utilize pulse width modulation. When you utilize pulse width modulation, you end up with much better power quality. You don't have low order harmonics. The first harmonic in bipolar PWM is the switching frequency, MF. What other harmonic content is available? MF, and then MF plus or minus 2. So plus or minus 2 harmonics. So it's if you're switching at 10 times the fundamental, then you will have the 10th harmonic, which is MF, and you will have 12, and you will have 8. Right? So you will have a 10th harmonic, 8th, and 12th, and then you will also have your fundamental. Right? You understand what I'm saying here? Okay, so if this is 10 kilohertz, the 10th harmonic, then this is 12, 8, and then this is fundamental. Okay? That's what this table says. And then you also, so the next harmonics you see at twice the switching frequency, 3 times the switching frequency, and so on and so forth. Okay? So 2 times MF, and then plus minus 2 as well. Right? So it's 20 kilohertz minus plus 2 kilohertz, for example. How about unipolar? Unipolar was even better. Unipolar, when we looked at the waveform, we saw it looked better, right? Because unipolar is utilizing the zero space, the zero states of the converter. Bipolar was just switching the output between VDC and minus VDC, VDC and minus VDC, and I was using that to create an average waveform. Right? How about unipolar? No, unipolar, I was oscillating the output between 0 and VDC, 0 and VDC, 0 and VDC, and then 0 and minus VDC, 0 and minus VDC to create my negative half cycle. Right? So it's a much better quality waveform. How do you see that reflected? You see that automatically reflected in the spectrum of the output. Right? So here, the first thing I see is my fundamental. And then what do I see next? Twice the switching frequency, not switching frequency. In bipolar, you see the next harmonic at the switching frequency. Here you see the first harmonic at twice the switching frequency, and then, twice the switching frequency plus minus 1 harmonic, or twice the switching frequency plus minus 3 harmonics. So if your switching frequency is 10 kilohertz or 10 multiples of the fundamental, then here you have 2 times 10 multiples of the fundamental plus minus 1. So 2 times 10, 20. So 19 and 21, right? So you see a harmonic at 19 times the fundamental and 21 times the frequency of the fundamental. And then so on and so forth for here. Twice the switching frequency plus minus 3 times the fundamental. Is this table clear? Where did we get this table from? Basically this equation for the bipolar, and there's a similar one for the unipolar in the textbook. And that's where they got the unipolar table. What do you notice? You notice that here this is 1, and then if I decrease the modulation index, my fundamental decreases linearly proportional. Right? We said that if I'm operating such that the peak of my modulating sine wave is less than or equal to the peak of my triangular waveform, I'm operating in a linear region. So, and I have a good picture to show later about this. But what I mean is, if this is my modulating waveform, and this is my carrier. As long as the peak of my sine wave is less than the peak of these triangles, then if I decrease it, I will get something less at the output. If I increase it, I will get something more at the output. So it's linearly proportional. And the degree of less or more changes linearly. Right? That's what we saw from the numbers, from the Fourier series expansion. Right? You can fill the numbers and look at it. If you have the numbers and the angles, you will see that they match up, and it's linear. There is another type of modulation where this is called linear modulation. And I have another picture later where I will show nonlinear modulation. I will show you later. Okay, so everybody's okay with this table? You see where it comes from? So you can calculate total harmonic distortion, for example, in voltage for bipolar and unipolar PWM for, let's say, a certain number of harmonics. Right? Yes, ma'am.
Sorry, you said, okay, so for this case, you'd find the first harmonics at two times the...
No, first the fundamental, and then the fundamental, and then after that it's twice the switching frequency plus minus 1 harmonic. So if the switching frequency is 10 kilohertz, or 10 times the fundamental, so if your fundamental is 50 hertz, then 10 times that is what?
5,000.
Is 5,000. So your MF is 5,000. What? 500. Sorry. So your switching frequency is 10 times your fundamental. So that's 500. How about twice your switching frequency? At 1,000. Right? So 2 MF is 1,000.
Okay. But how would you find the ones at 4 MF and 6 MF? Would you ask us to do those, or?
What do you mean?
Like if okay, so we find.
They're giving them to you here.
Oh, I mean the ones like on the graph, because we have the ones for 2 MF plus minus 1 plus minus 3, right?
Yeah.
But then beyond that, for 4 MF plus minus 1.
Yeah, they didn't tabulate them yet.
Would you ask us for that, or?
No, if I give you this equation, I can ask you. If I give you this equation and I give you the angles, the corresponding angles, then I can ask you. If I don't give you this equation and I just give you this table, let's say I ask you to start from this table and calculate total harmonic distortion for the fundamental for everything up to the MF plus minus 2. You can do that from this table. But beyond that, you would have to fill this table using this equation. Which means I would have to give you the angles corresponding to every single pulse.
Yeah, okay.
Right?
Okay.
That'll be too tedious. As long as you know how to do it, yeah. I think, yeah. I hope so. Let me see. Yeah, it's recording, yeah. Yeah, it's still recording. Only when I press stop does it stop recording. Okay. So that being said, so here then they show some simulations for, bipolar PWM. Again, the output is oscillating between the output of minus VDC and minus VDC, and you see the harmonic content, right, in the current waveform, right, and then they do the same for, I think, the bipolar PWM. Now this is also bipolar. This is, but here, what did they do? I think so. They made the modulation index 0.9, the frequency modulation, the amplitude modulation index 0.9, and the frequency modulation index 21. How about the previous case? They don't tell you the. So the frequency modulation index controls what? The switching frequency. Right? It's the frequency modulation index. The definition, if you look at here, is the frequency of your triangular waveform over the frequency of the sine wave. Right? So if the frequency of the triangular waveform is 21 times the frequency of your sine wave, so your sine wave is 50 hertz, MF is the frequency of your carrier or your switching frequency would be 21 times 50 hertz. Right? That's MF of 21. So they're just showing some simulation results and nothing very specific here. You just need to know that, for bipolar versus unipolar, where is the first harmonic after the fundamental? For unipolar, it's at twice the switching frequency. For unipolar, it's at twice the switching frequency, plus minus 2, and then plus minus 3. For bipolar, it's at the switching frequency, right? Bipolar. Obviously, here they've improved what? They've kept the same modulation index, right? 0.9 is the modulation index. 0.9 is the modulation index, but they've increased your frequency modulation index. Increase the switch frequency modulation index, which means I've increased my switching frequency. Which means what? It's like sampling your waveform a lot faster, right? In signal processing, it's like sampling. So you expect to get a better waveform. This waveform definitely is closer to a sine wave than this waveform. This has a lot more ripple, right? And it makes sense because remember, this is an RL load. RL load, if you keep a voltage on it, what does the current in the inductor do? Rises like a rectangle. Or the voltage is negative. What happens here? The voltage is negative for this period. Current falls like a straight line, with a ramp. So positive current, positive voltage results in a rise. Right? This is positive voltage across the RL load. Here, negative voltage across the RL load. It's going down. Right? So the duration of this, of course, will control the amount of ripple that you have in your waveform. So if you make this very small, then you have less time for current to rise and less time for current to fall. So you end up with less ripple when you increase the frequency modulation ratio. Okay? Does it make sense? Of course, at the expense of power loss. Right? If you increase switching frequency, it means you're increasing this at the expense of power loss. Something you have to assess. And this is unipolar pulse width modulation. And then three-phase inverters. So let's look at that. So everybody's okay with this discussion on power quality, etc.? Yes. Yes. Yeah. This is what you want to see at the output. This is your modulating signal. Yes. So 50 Hz, 60 Hz, whatever you want. If it's for a motor application, you're controlling the frequency of that and the voltage, right? So you're controlling the frequency of your modulating signal, as well as your modulation index in that case to control V over F. Right? Okay. So everything we talked about, of course, we mainly talked about the single phase, half bridge, and full bridge inverter, but you can easily extrapolate that to three phase. And the discussion is very similar. I mean, if we discuss it we talk about it from the same perspective of what I like to draw here as the single pole double throw representation of a switch. Remember, we always said that these two switches will have a stiff voltage across them, right, and a stiff current at the output, right? And the three-phase inverter doesn't differ at all, right? Here there's stiff voltage across the two devices, and then there's a stiff current here at the output. And this is for one phase, another phase, and the third phase. right? So same as the DC converter, exactly. So what is the average voltage here? And here, and here. With respect to these, the reference here. What is this average voltage? If this is controlled by duty cycle D1, D2, and D3, what is this average voltage?
Duty cycle times Vn.
Exactly, it's duty cycle D1 times Vn. Here, this is duty cycle D2 times Vn. Duty cycle D3 times Vn. They're it's the same. Power converters are all the same, right? So you can operate this to create DC if you want, or you can make it create AC, whatever you want, right? It will depend on D1, D2, and D3, right? In a three-phase inverter, we would like to create AC at the output here. So let's say I will try to draw my duty cycles, right? This is 0. Duty cycles range between 0 and 1, correct? And then if I control D1 to look like this, right? And then I control D2 to be 120 degrees apart and look like this. Right? Then this is D1, blue is D1. Blue is D1, red is D2, right? So what do I see between these two nodes? What is the voltage that I see between these two? I see D1 times Vn minus D2 times Vn, right? You agree that this is the line voltage now between these two? D1 times Vn is here, and D2 times Vn is here, right? So I see Vn, D1 minus D2. This is what I see. I can control D1 minus D2 to be anything I want. If I control them to be two sine waves that are 120 degrees apart, what do I get? We know that if I have a sine wave, like the phase voltages, they are two waveforms that are 120 degrees apart. What is the line voltage equal to? VA minus VB, for example. What is that equal to? It's sine wave as well, square root of 3 larger, and phase shifted with 30 degrees. Right? So I can control D1 and D2 to be sine waves that are 120 degrees apart. I create these, right? These are reference values. I create them from my controller, right? I can do that. So you do that and you make them look like sine waves. Right? If you make them look like sine waves, as long as they between, if you look at what's happening to the difference between them, look at D1 minus D2. D1 here is a positive value, here is a smaller positive value, so you get a positive value. At some point we have to make sure that we are seeing negatives. Do we see negatives or not? Yes, D1 is less than D2. And do we see 0? Yes, at points they are the same. So these are the 0 crossings, obviously. And then whenever the red is greater, I'm getting negative. Whenever the blue is greater, I'm getting my positive waveform. So I will end up with a waveform like this. And this is going to be D1 minus D2 waveform, which is going to be square root of 3 larger and phase shifted with respect to D1 and D1 and D2. Okay? And I can do the same with D2 and D3. Right? I want the voltage here to be what? This voltage would be D2 times Vn minus D3 times Vn. So you would create a D3 that will be 120 degrees phase shifted from D2. D3 here will be 120 degrees phase shifted, so that I have a three-phase sine wave. And these two will be like VAB, and this would be like VBC in a three-phase system. Right? But this is exactly the same knowledge that we used for chapter 6, the DC-DC converter. Okay? Okay, so what is the peak value of the line voltage?
Or just D1 or D any of them?
If D1 is 1 and D2 is 0, it's Vn. Can it be greater than Vn? What's the peak value? I'm just saying, what's the peak value of Vn? It's Vn. So what's the peak value of VAB? My line voltage maximum value can be Vn minus D1 times D1 minus D2, right? So this will be peak value of Vn, and minimum value minus Vn. This is 0 and this is 1. Duty ratio will always be between 0 and 1, right? That makes sense. We know that for my, like, if you exclude this third leg, what do I have? I have a full bridge converter, right? Exclude the third leg, and I have a full bridge inverter, so right? For the full bridge inverter, I get output between Vn and minus Vn, right? And that's what we have here. We're okay with this? And then calculation of losses, everything is very, very similar. Fine, here the duty ratio is very different than DC converter. DC converters, you typically at a fixed duty ratio. Here, if you want to be very precise in calculation of losses, you have to account for each pulse and each pulse width because the duty cycle keeps changing. Or you can just assume a certain average value for the pulse width and calculate losses at the back of envelope type calculation. Right? You don't have to be very precise because it's already off. But
So
you,
that's the maximum of the line voltage, right?
yeah, maximum of the line
What
voltage.
about the maximum it's related to the pulse.
Maximum of the phase voltage will have to be related to the type of load that you have. This is a star connected load, so the phase voltage here will be square root of 3 less than the line voltage. Right?
That's
Yeah.
related to what we did previously.
Yeah, it's exactly. This is a 3-phase star connected load. So the line voltage I can calculate. What is the phase voltage? The phase voltage is the voltage between this node and this node. How do I calculate that? Circuits. So it will be square root of 3 less, and the phase shift will be 30 degrees. Okay? We will see. I will draw. This is sinusoidal pulse width modulation for a 3-phase inverter. Right? I jumped a little bit. The textbook takes you through the 3-phase inverter a bit slower. Right? So they go through the single pulse example like we did for the full bridge. They go through something similar. But I think we have the background to look at the sinusoidal. But anyway, let's go through what they're doing. So this is a sample 3-phase inverter with 6 switches. The simplest way you can control it is, again, a single pulse for each of these devices per cycle. So, and that's called 6-step operation, because you have 6 switches. If you activate each switch 1 time per cycle, it's called 6-step operation of a 3-phase inverter. So, how does this 6-step operation work, and what do the waveforms look like? And then, how do you build towards do we see the reason why we would go to sinusoidal pulse width modulation? Again, it's because of harmonic content. So let's look at the 6-step operation. So the 6-step operation, we said that we will operate each pulse for a certain period of time at 120 degrees. 120 degrees, you keep each pulse on for 120 degrees. And you phase shift the pulses by 60 degrees. So let's see what happens. If I have, let's look at this case here. This first case here, or first switching state, I have what? S1 on, S5 on, and S6 on, right? S1, 5, and 6. And let's look at what the corresponding phase voltage will be and the corresponding line voltage will be, right? 1, 5, and 6 on. So let's go back to here. If 1, 5, and 6, what is the corresponding phase voltage and what is the corresponding line voltage? So 1 is on, 5 is on, and 6 is on. Right? So what is the equivalent circuit that I can redraw? This looks like what? I have my battery here, and then phase A is connected to the top, and phase C is also connected to the top, right? So phase A here, and phase C, phase A, phase C, connected to the top. How about phase B? Bottom. Right? So what is the voltage across phase A and C, because they're in parallel, and what is the voltage across phase B? Assuming the resistors are the same, assume these are resistors and they're all the same, then this can be simplified into what? This is R over 2, right? They're the same, right? In parallel, and this is R, right? So what is the voltage across R, and what's the voltage across the R over 2? VR is equal to VDC times R over R plus R over 2, right? Which is equal to what? R over 3 over 2R, right? So it's 2/3 VDC. VR is equal to 2/3 VDC. We agree? So this is 2/3 VDC. How about this?
Just 1/3.
1/3. If this is 2/3, this is 1/3, because I have here VDC, right? So anytime, so this one will have 2/3 VDC, this one will have, so what's the voltage across phase A? 1/3 VDC, right? So, and then if I change the switching state, and A is, instead of B, it will have 2/3 VDC. How about if I flip the polarity? If B is by itself, is alone as well, phase B is connected to the top, and A and C are connected to the bottom. Then what is the voltage across phase B? Minus 2/3 VDC. Right? So you have to keep a polarity, right? You have to assume your polarity is something, right? So if you're assuming that the polarity is such that you're going from the phase B to the neutral as positive, if phase B goes to the top, and you're going from the phase B to the bottom here, and you get a negative number, then it's a negative value, right? So it's either 1/3, 2/3, negative 1/3, or negative 2/3. That's the voltage across any of the phases. Do you see that, or yes? So let's see. So as we expected here, the voltage across phase A was 1/3 VDC. This is the phase voltage, right? Phase voltage was 1/3 VDC. Again, you can now go through the switching states. Each of these switching states, we went through one of them. We went through the first switching state where 1, 5, and 6 were on. Go through the next one where 1, 2, and 6 are on, and you will see, and go do the similar exercise, and you will see that across phase A, now I have 2/3 VDC. And then I go to the next switching state, I get 1/3 VDC, and so on and so forth. And this is phase A voltage with respect to neutral. Phase B voltage with respect to neutral. Phase C voltage with respect to neutral. How about my line voltage? The difference between them, if VAN minus VBN will equal VAB, right? So if I take here, this is what? What's VAN? 1/3. How about VBN? Negative 2/3. So VAN minus 2/3 is equal to 1, right? So VAB here is 1 during the first switching state. Okay? Do we agree? Do we see the relationship between the switching pattern, the phase voltage, and the corresponding line voltage? Okay, so this is the simplest, three-phase inverter. What do we get here? We get exactly the single pulse per cycle type waveform that we saw before for the single-phase inverter, right? And why did we want to go away from that? We went away from that because that produces the output power quality that we don't like, right? But this is a way to get three-phase output. The 6-step operation of a three-phase inverter is the simplest way to do it. What can we do to improve it? Everything we talked about before, we can repeat here, right? We can make each phase a set of single-phase inverters in series. Or we can just use multiple pulses per cycle like we were talking about in sinusoidal PWM, right? So So typically that's what we would do. So again, of course, after we draw these waveforms for phase and line, how do we judge these waveforms? Using Fourier series, right? So here they derive the Fourier series for the line-to-line voltage and the line-to-neutral voltage. So this is the peak value of the line-to-line voltage harmonics. And this is the peak value of the line-to-neutral voltage harmonics in this three-phase, six-step inverter. So if I ask you to calculate the THD for up to 4 harmonics, you would use in the line voltage or the neutral or the phase voltage, right? You'd use these two equations. Okay? Okay. Again, you will not have to derive the Fourier series. You will just use whatever they have. Okay, so again, because of the poor power quality, because here you will see 5th harmonic, 7th harmonic, 11th harmonic, which are low order harmonics, and we don't like that. We would like to see only high order harmonics because we can easily suppress them using simple filters. Then people started using multiple pulses per cycle. Multiple pulses per cycle in three-phase inverters can go through the same logic we did before. You can add 2 or 3 pulses that you calculate offline. You can do that. Or people have advanced to the level of understanding sinusoidal PWM better and understanding this concept of changing the modulation ratios or the D1, D2, D3 the same way we varied them, and how this creates an output voltage waveform that looks like a sine wave. Looks very well like a sine wave when you average it out through a filter, right? So that's called sinusoidal PWM. And we discussed that for the single-phase inverter, and we discussed it at the beginning for the three-phase inverter. And here they just show you the fact that, this is the carrier. The triangular is my carrier waveform, and I'm intersecting the 3 duty ratios: VA reference, which is my duty ratio for phase A; VB reference, duty ratio for phase B; and VC reference, duty ratio for phase C. Right? So what do I get? I get at the output, my line-to-line voltage is something that looks like this. Again, you can go through, look at power quality, and how do you do that using Fourier series. So they do the same thing. How do they calculate this? So this is the AN and BN harmonic components for a three-phase sinusoidal pulse width modulated inverter. So this is the voltage harmonic N for a three-phase inverter, and you would calculate it by calculating the corresponding ANs and BNs. Right? It's all about power quality. Inverters is all about, how do you differentiate between sinusoidal PWM and, programmed PWM. So where you've programmed a few pulse widths, you differentiate between them with the harmonic content. How do you look at harmonic content? Fourier series, like we did just here. Yes, ma'am.
So, those formulas,
Yeah.
not in the sheet. Do you want us to know them?
They're not? Chapter 8?
Yeah, the last,
Yeah, the phase and line are there, but these two are not.
yeah, the AB and
Okay.
the ones beforehand for the pulse 6 step 1.
Okay.
Then,
It's fine if it's not there, it's not there. If we need it, we'll add it.
okay.
I mean, they're the same, right? The idea is the same. Here it's... But what's different here, actually? What's very different? Huh?
Why is it N3? Means 3-phase?
Yeah, it means three-phase, but also this is like unipolar PWM. So it's not like the previous case. The previous case, they gave you 1, 5, 7, 11, blah, blah, blah. How about here? Do they need to give you 1, 5, blah, blah, blah? No, they don't, because the first harmonic will be like the unipolar case at twice the switching frequency. So I don't need to worry about it. So you just need to worry about the value of your fundamental in this case. If you want to really compare, different types of modulation, then you need to look at the higher order harmonics. But here, the first harmonic after the fundamental would be at the switching frequency, at twice the switching frequency, because this is like unipolar PWM. The line voltage is like unipolar PWM.
Should be very small.
What?
Should be very small.
Yeah, it's small and it's high frequency, so you should be okay. That's why pulse width modulation is great. I mean, people would like to use it, but you will be limited in how many pulses you can add per cycle by the number of by the switch that you choose, and the switch that you choose will depend on the rating of the equipment that you have. So if you end up with a very slow switch, 2-3 pulses per cycle, then you really have to calculate the Fourier series, because then the power quality will be an issue, and then you will have low order harmonics that are an issue. But if you're able to switch high enough and get many pulses per cycle, then you don't have to worry. Right? But sometimes your switching frequency for these high power converters is 500 hertz. 500 hertz is a very small value. I mean, when your fundamental is 50 or 60, and you're switching at 500 hertz. Right? It's a very low switching frequency. Some of the mechanical systems or the mechanical components, or even some of your electrical circuits, may have a resonant frequency around that much. And you want to make sure that you're away from the resonant frequency of any of the components that you have in your system. Because if you have a voltage harmonic, it's a small value, but it happens to be at the exact resonant frequency of a circuit in your power system. And what's going to happen? You will excite that resonance. Right? Resonance is what? Resonance means what? Resonance means it's an impedance that sees a harmonic at a specific frequency that it is tuned for, and at that frequency it becomes a very low impedance because the L and C cancel each other, and it's a small resistance in that case, so current will flow, huge current will flow. So even if you have low harmonics, but if they correspond to a resonant frequency in your system, the generator's resonant frequency, the transmission line's resonant, whatever, if any resonant frequency in your system, you have to, that's why when you design any mechanical system or electromechanical system, you have to know the resonant frequencies of all devices in your system. So power system studies, there's, people that took 459, we conducted a load flow study. A load flow study is one of the studies that you typically conduct for a power system. You want to know the rating of equipment. So you conduct a load flow. Okay, you want to know if when the motors start and suck a huge amount of current, motor starting is, induction motors start with a high current. So what happens when you have high currents for a short period of time? High currents means big voltage drops. Big voltage drops correspond to low voltages on equipment in your power system. Can your equipment operate safely with a low voltage? You have to conduct that study. So that's another kind of study that you conduct in a power system. Harmonic resonance studies is another kind of study you conduct in a power system. You want to make sure that your system is safe at various harmonic frequencies. So you're switching, for example, you're switching at a certain frequency. You're expecting there should be harmonics in your power system at that frequency. So you build a model of your power system and excite that model with that specific resonant, that specific frequency that is in your system. What will happen? You look at that system. Okay, are currents going to increase very much? Am I going to get high torque pulsations in the generator? So that's another study that you conduct. Right? So there are various studies that you conduct in a power system when you're designing one. Yeah. And these numbers tell you the values of the various harmonics that you're going to put in the system when you use a three-phase inverter switching using a six-step mode, or using sinusoidal PWM mode, or other types of modulation. Right? This is where you get the numbers that you take and calculate and plug into these harmonic studies. So this is very practical when you think of a large system. Okay. Again, we talked about multi-level inverters before, and again, you can apply lots of modulation techniques to multi-level inverters as well. We will talk a little bit more about that. I have another slide that's interesting, another set of slides that I'll show you soon. Yeah. Applications of DC to AC inverters. Of course, we know motor control is the biggest application of DC to AC inverters. We understand that we need to control V over F ratio to be a constant in order to control the torque speed characteristic, right? If we don't control V over F to be a constant, then I get this. This is green. The green is change of V only. V only being changed. The green is V only being changed. This is all the same motor. All the same motor. This is all the same motor. The same motor here, I've changed the voltage. V1, V2, V3. Right? Here I can get a minor change in speed. Right? This is speed. Minor changes in speed. Right? Very little changes in speed. So changing voltage by itself will not change the speed of a motor. changing the V over F ratio will move this whole torque speed curve to the left or to the right, right? And that's why you want to change V, which is going to be changed using the modulation index, amplitude modulation ratio, right? This is the V, the voltage of your sine wave over the voltage of your triangular waveform, right? This is the modulation index. You change that way. And then this F, how do you change it? You change it by changing your reference voltage. Your reference for D1, D2, and D3, you change the frequency of those to change F. So you change both to maintain a fixed V over F ratio so that you can create a certain flux in the air gap. Right? So that's a big application of DC to AC inverters. And this is a block diagram of a more detailed DC to AC inverter. So this is what the three-phase SCR based rectifier. So here I can control my DC output voltage using the thyristor bridge with a thyristor rectifier, and then I can take this DC converted to AC into the motor. So this is the most common application. So this really ends the chapter. I want to touch upon this set of slides. I also have it on your website. This is more of a discussion. This is give and take, just some pictures of stuff and some interesting things. I don't know if I went through some of this or not. Did I at the very beginning? So switches come in many packages, right? So this is, for example, this is example of a high power semiconductor switch. In your phone, you have a switch as well. You have MOSFETs and BJTs and IGBTs. So depending on the power rating, the silicon itself is large, as well as the packaging differs, right? So this is called a power pack. It's not a power pack. This is called module. This is a module. This is a power pack. One second. This is a power pack, and this is a module. So this power pack, devices you can have a thyristor or a diode. Typically are given in power packs, and I'll show you how to stack them up when you use them. But so these modules, inside these modules you can put diodes, thyristors, GTOs, any type of silicon you put inside these modules, right? And it will typically have a metal base, so you can put it on a heatsink, right? This is the power module here. Again, device rating, as we said, is a big consideration, and that's why you cannot infinitely choose. I want to create a IGBT inverter for 10 megawatts. Okay, what is the voltage level? Let's say you're talking about a voltage level of 10 kilovolts. If you're operating at the voltage level of 10 kilovolts, the only device that can work is an SCR. That's what this sort of chart is showing you, that this is voltage level and this is current, right? At low values of current, IGBTs work. IGBTs work in this blue area. And these are the various IGBT ratings from the different manufacturers, right? So there are IGBTs for 1,000 volts, 2,000 volts, 1,000 amp, 2,000 volts, maybe 1,700 amps. But if you want to go higher current, you will not find an IGBT. So if you don't find an IGBT, that means you cannot use sinusoidal pulse width modulation and switch it many times per cycle, because you're going to end up trying to go to a GTO type device. We will look at the speed of this GTO, or these GTO is basically what? A thyristor that we sort of converted to be able to turn off as well. I think I briefly touched upon that at the very beginning here. So we will look at the speeds of these devices, but generally, and MOSFETs will be right here. Right? MOSFETs operate in this range, so up to 2,000, up to 1,700 volts. Actually, you will find some MOSFETs. Very rare, but you would find some, and then currents much less. Actually, I should do this. Maybe up to 100 or 50 amps. You would not find high voltage. Actually, maybe more like this. Right, so it's low voltage, high current, up to maybe 1,000 amps or 800 amps, MOSFETs. But you cannot find a MOSFET that operate maybe here, almost 800 amps and 1,000 volts. You would not find it. Right, so, and MOSFETs are the fastest device. Right, so if you want to create many pulses per cycle to improve your power quality, then you would love to use a MOSFET, but you can't. If you operate here, you're limited to what? You're limited to this black is the GTO, GCT type device. or an SCR. That's it. These are the only two devices you can operate at in this range. Right? That's why these multi-level topologies became very interesting. Because with multi-level topologies, what was the benefit of multi-level topologies versus the classical H-bridge or three-phase inverter, single level? What's the benefit that we get besides improved waveform quality? What was the benefit on the switch voltage rating?
Yeah,
It was half, half for the three-level inverter, and then it became 1/4. Depending on how many levels you add, the voltage rating becomes less and less, right? So what does that mean? It means I can build a higher voltage converter now with an IGBT, but it's not a single IGBT anymore. I have to use a multi-level inverter topology, or I have to use IGBTs in series, right? And I talked briefly about why don't we like to use IGBTs in series, and I will show that here. Anyway, this is called a press pack or a power pack. This is a power module, and typically, this black is a heatsink. The press pack has metal on both sides, so you can cool it on both sides, right? And it's easy to cool diodes on both sides. And the modules you would have to put on a heatsink on one side, right? So you probably find press packs at a higher current rating, obviously, because you can cool them easier than a power module because you only cool it from one side. The more surface area you have for cooling, the better, right? So examples of thyristors, 4,000 volt, 800 amp, and a 4,500 volt, 1,500 amp thyristor. Waveform thyristor. This is the gate pulse current, and then this is the thyristor current, and then this is the reverse recovery. Thyristor is a diode, right? Thyristor is basically a diode. So there's a reverse recovery time, and a corresponding reverse recovery charge that we talked briefly about initially about diodes, right? So that thyristor is the same. It's nothing but a PN junction, but with a controlled fashion, a controlled gate, controlled turn on. This gives you some thyristor characteristics. To turn off a thyristor, turn it on and off. It turns on pretty quickly, but it turns off 1,200 microseconds. Do you remember the exam? What was the turn off time? You don't? 100 what? Nanoseconds. Yeah. But nanoseconds. We were talking about nanoseconds here. Right, so we were talking about 100 nanoseconds versus 1,200 microseconds to turn this thing on and off. Right, so how fast can you switch? Right, this will limit how fast you can switch. Right, so if you want to create a certain duty cycle, obviously you're going to be limited to a few pulses per cycle. Right. Just more devices. Another device. This is the gate controlled thyristor. So this is a thyristor that we're able to turn on and off like a MOSFET. Remember, thyristors you can only turn them on, and then they turn off when the current tries to reverse, right? And then we added another thyristor variation of that called the gate turn off thyristor. So it's a thyristor we can turn off with a gate pulse, but current controlled gate pulse, which was also not very nice because I had to maintain current, and current had to be high. It had to be a high current to do that. So then people developed what is called an insulated gate commutated thyristor. So it's turned on and off like a MOSFET by just applying a voltage and charging a gate capacitance. So it's easier to turn on and turn off. It's a basic thyristor you can turn on and turn off, but with a MOSFET front end, if you think of it that way. So this is really nice. Very nice device, but it's huge. It's like all of this is electronics to make it happen here, right? So it's a very complicated device here. Obviously very expensive.
So it's like just a pulse instead of constant.
Yeah, it will be like a MOSFET. You will apply a constant voltage, but the current will be what? You're just charging the gate capacitance, like a MOSFET. BJT devices, you need base current, continuous base current. MOSFET devices, you just need a gate voltage to charge the gate capacitance. You apply voltage, capacitor is charged. That's it. You're not sucking current anymore. BJT devices, you need a base current all the time to keep the device on. Right? So the GTO is like a BJT type. Turn on and turn off. right? The GC, the integrated gate commutative thyristor, the IGCT, was like a combination. It's like a MOSFET gate, but thyristor power device. So very nice device, very expensive, very useful for high power. Of course, the workhorse is the IGBT. Obviously, I mean, it's a very nice device because you can switch very fast. And let's look at this here. So here we're talking about 0.2 microseconds, or 0.2, 0.3 microseconds versus the 1,200 microseconds for the thyristor, right? Do you see here why I can use this with many, many pulses per cycle? It just turns on a lot faster and turns off a lot faster, right? Of course, you can use these IGBTs in series, right? You can put devices in series to cause big voltages. If you want to turn off and turn on large voltages and you don't want to go to a thyristor, what do? You want to put many pulses per cycle. You can put IGBTs in series, but it has problems. What are the problems? It's voltage unbalance. So you're turning all of these on at the same time. What if one is turning on a little bit later than the others? Then one is going to carry the full voltage for a short period of time. You lose everything. There's no benefit anymore of that. So voltage unbalance is an important criteria here. So what do people do to tackle this voltage unbalance thing? So they use either passive sharing circuits. They put circuits around the device. Again, we're not going to get into the details of the design of these circuits, but what these circuits do is, they sort of keep pushing. They try to maintain the charge across these capacitors equally. By designing this circuit in a certain way, you will be able to control the voltage across this capacitor such that you're sort of making all the devices see the same voltage when they are, turning on and turning off. Right? It's like a stiff voltage across the switch. Right? Capacitors create a stiff voltage, right? So here it's like having 3 capacitors each across the switch, and you're able to control the value of the voltage across the capacitor using proper selection of RS and RV. What is the disadvantage of something like this? More circuitry, and then there are resistors and power loss, right? And here I'm talking about power, high power currents flowing through. This is the voltage across the switch, very high voltages, and the currents that are moving around here are the currents that are fed from these high power switches as well. So it's a high losses. Losses are an issue here. Another way to do it is by controlling the gates. You have 2 devices in series. You have complicated now gate drives to make sure that this doesn't happen. So if this is the 2 devices turning on at different times, right? Here 2 devices turning off at different times. So these these circuits here, they would measure, for example, the voltage across the switch. What is this doing? This is measuring the voltage across this switch. This is measuring the voltage across this switch, doing some processing around it, blah, 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 and then altering the gate signal. So this is the gate signal. This is the gate signal coming in, amplified, and then what's happening here? This gate signal, before it goes to the switch, is being altered by this circuit. What is this circuit doing? It's a detail we don't care for now, but basically what it's doing is making sure that if the voltage across this and this are different, then it makes one greater than the other, so that the voltages are equalized. The objective is to make the voltage across this device and this device equal all the time, right? So that's why it's like a controller, right? It's like a controller that, but here with positive feedback or negative feedback, depending on the detail we don't get to, but the idea is it's going to alter the gate signal to make sure that the voltage across the device is the same, right? What else? We talked about multi-pulse diode rectifiers. What is the advantage of those? Huh? Yeah, less ripple at the output. And what else? Yeah, less ripple at the output. That was the main thing, as well as higher voltages. If you want to put high voltage, if you have a high voltage output that you want to create, and you don't want to put series devices, so you can create these multi-pulse rectifiers, and they will improve the output power quality. What else do they do? Let's look at I think they show the input. I think they also, so I don't think we showed that in what we discussed, but they also happen to reduce the input, improve the input power quality as well. One thing also we didn't stress upon is, I think we did the full bridge, three-phase full bridge rectifier with a resistive load. If I go back to the slides that we did, right, we did the three-phase AC to DC converter with a resistive load. But we didn't put, a capacitor, or we didn't put a DC source, for example, right? So what does the current here look like? We said that the current in phase A, the current will look like what? So here and here, phase A is conducting. So current will look like, right? This is phase A current. Right? This is phase A current, right? A is conducting, so obviously I have current. A is conducting, A is conducting.
There's BA before
Yes,
CA.
What?
It's select shift with the it's at 3, 4 and 4.
What, come again?
It's at 3, 4.
3, 4, and 4, 5? 3, 4, and 4, 5. This is more than one cycle, I think. Yeah, this is more than one cycle. This is one cycle of the fundamental here, right? Yeah. This is one cycle of the fundamental. So this is one cycle of the fundamental. So I will have but this will be phase A current will be like this. Right? We saw. I mean, we draw it on the next page anyway. The next slide. Here. Here. So this is phase A current. Yeah, phase A current was this double hump thing here I have, right? So what happens if I add a DC source at the output? We didn't go through that when we were talking, but I found it in this set of slides here. But what happens if I add a DC source or a capacitor basically at the output? Let's say DC source, a resistor and DC source.
And like in series with a resistor?
Let's say I add a DC source at this level.
Are we talking about the DC-DC conversion?
AC to DC rectifier, AC to DC rectifiers I have a resistive load with a DC source.
What will be shifted?
What will be shifted? No, the output will not. The output voltage will not change. The output voltage will not change, but the current will change. Now the voltage. Okay, you have a rectifier.
Removing the DC value.
Exactly. So this is my three-phase rectifier. The three-phase rectifier will still produce my 6 pulse output. 1, 2, 3, 4, 5, 6. And then I have what? And then I have my resistive load. And then I have a DC source. So what is the current that's flowing through this? The voltage that will not change. Right? What will change is the current. Because what's going to happen here? The current that's going to flow, instead of looking like this, it will look like what? Maybe come down to 0. It will reduce. I mean, the current will reduce a little bit. I mean, the value of the current will reduce. It may reduce to a point where this, this dip here gets to 0, right? It's just a detail. I mean, if you keep reducing this current, what happens? You keep reducing this current. This dip is lower. Right? At some point, you may cross 0. I mean, it's just a waveform that they had drawn here, and I didn't show you before. So they had it drawn here, and I didn't show you before. Like this is phase A current, phase B current, phase C current. Instead of these two humps being up high, they added a DC source here. If you add a DC source, what happens? You're reducing the current. You're opposing the current coming from your input rectifier, basically. Right? I'm just showing you some pictures of some interesting waveforms having a discussion here.
Sorry?
Yeah.
If the current is at 1.0, why won't the output change?
Why won't the output? What do you mean?
The output voltage, I mean, the shape. That's the, I'm assuming that's the output current, right? Or is that the?
Yeah. If there's no current, and you're measuring the output will be DC. The output. Remember, what was the output looking like? The output was. You have this 6 pulse coming from your 3-phase rectifier, and then you had a DC source.
Mm-hmm.
At these places where the DC source is high, the current decreased considerably. So assuming that the current was 0, the output will look like, like this, here, like this, here. Since there's no current, then the output voltage will be the DC source, right? So instead of following the input, right? There's no current. If the output is measured across my resistor and my DC source, so when there's no current, the output is the DC source, right? So, again, I don't expect you to be able to calculate the harmonic content of it. I'm just going through some general stuff and trying to relate it, and I'll show you some. Oh, we're done. Time is up. I'll try to show you some other, some nice pictures. Yeah.
So in the clean sheet, there's a typo, which makes the equation wrong.
What do you mean?
Yeah, so the current, the negative
Minus
is not in the power, it's out, it's like.
It's just minor.
What?
It's very minor. This one makes the.
It's just that. Oh,
Okay. Can you send that to Sam? Ask him to CC me. Send it to Sam. I'll tell him there's a mistake there,
okay.
and ask him to. But CC me, please. Okay.
Do you want me? Should I just email him a blank email with this, or do you want me to say?
Yeah. Just show. I mean, show him. Take a copy of this and show him this is a mistake.
Okay.
Please correct it and CC me.
Okay.
Anyway, guys, just go through this set of slides. It has some pictures of multi-level inverters and some waveforms, and this is a multi-level inverter composed of several cascaded bridges. Again, just some practical stuff that has some interesting sort of consequence. And then one thing I want to show is overmodulation, guys. Just one second, give me a little bit. So here, my triangular waveform. This is my carrier waveform, and this is what? This is my modulating waveform. These are my sine waves, right? Here, these sine waves are a lot higher than this triangular waveform. So what am I doing here during these periods of time? I'm just saturating. I'm not changing, not switching anymore. This produces a higher RMS or lower RMS? Higher, because I don't have the zeros. RMS is basically proportional to the area under the curve. So here I have larger area under the curve because I'm not bringing down this to 0. The problem with this is, of course, you get more harmonics because you don't get many pulses per cycle. You get more harmonics, higher value of voltage. So people try to work around this and figure out ways to do it. So how did people go around this? Something called third harmonic injection. Here, what am I doing? This is now my modulating waveform. Not a sine wave anymore. It's a sine wave with a third harmonic added to it. It's like this third harmonic added to this original sine wave. What does this do? It brings the total to dipping here at the middle. Why is this good? This is good because my triangular waveform, which is still limited to here, will intersect with this waveform here, right? All the time. I'm not saturating anywhere, right? And then you never see third harmonic in the line-to-line voltage. Remember, in line-to-line voltage is what? Phase A voltage minus phase B voltage, right? Third harmonic. Do you remember our discussion about third harmonic? Third harmonic for phase A, third harmonic for phase B are in phase, right? We discussed that, I think, at the beginning of the class. So if you subtract phase A minus phase B, do you see third harmonic? I don't see third harmonic. That's why here we came up with a modulation technique called third harmonic injection, or people manipulated it later to call it space vector modulation, right? And what this does is allow you to continue to intersect with your carrier frequency so that you continue to create a nice harmonic content. At the same time, better utilize your DC voltage because you can produce a higher value of RMS voltage. Right? So you can utilize a higher value of RMS voltage, but you don't see poor quality and output. Your line-to-line voltage, third harmonics are subtracted from each line-to-line voltage. Phase voltage has third harmonic. Another phase voltage has third harmonic, but the line voltage doesn't. What are you applying to your loads? You're applying the third harmonic. Right? You're applying to line-to-line voltage. So your loads will never see third harmonic. So you have good power quality, better utilization of your DC link or your DC value. And this is, this came from the idea of third harmonic injection, but people later, came up with a way to standardize it, and they called it space vector modulation, sort of a mathematical manipulation of this third harmonic injection called space vector modulation. So again, go through the slide just for general knowledge. I mean, this would be very practical stuff if you ever work on these kind of things. Yeah. So I'll stop here. I hope you learned something. So.